Dr. Jan Rainer Lahmann. He is passionate about quantum computing since 2017. And especially his focus is on algorithms, relevant use cases, and the potential value of quantum computing. He leads key quantum computing initiatives at IBM in the DACH region and is a member of the prestigious IBM Academy of Technology. And with that said, Jan, stage is yours, and please give him an applause.
So, yeah, thanks a lot for the kind introduction, Luise, Jan, and Mira. So, if you could change the presentation to my one. And yes, I would like to speak about the current status of quantum computing, especially at IBM, and about the path to quantum advantage. Yeah? And that already implies that we strongly believe that quantum advantage has not been achieved yet in the industry in total. And I would like to describe the path that we see to reach that. And still waiting for the charts. So, and maybe with that, I can start with trying to define what quantum advantage is for us, because there are different like opinions or. Okay, so apologies for the difficulties. The presentation is missing currently. But yeah, maybe I start to describe some of the aspects that I wanted to discuss. So first of all, I said quantum advantage has not been achieved yet. And obviously, at some point, we need to, as in quantum computing industry, we need to achieve that, because otherwise people would stop caring about quantum computing. And the definition, or what we understand as quantum advantage, is we at IBM, we always speak about practical quantum advantage. Yeah, so practical industry-relevant use cases, yeah, where with using quantum computers, an advantage, and that can have various forms. Yeah? So it can be that you can solve larger problems than with classical computers alone, that you can solve the problems faster, that you get more accurate results, or that you need less energy for the computation. Yeah? All of that, so any of these or a combination, that is what we understand as quantum advantage, and always for practically relevant use cases. Okay, so then let's speak about the areas, yeah, where we see quantum algorithms and where quantum computing can be applied. I think that has been mentioned before here on the stage. So we see three large areas. One is simulation of quantum mechanical systems, yeah? So like quantum chemistry and material research. There are some examples of partners that we are working with in that area. One example is Bosch, and they are doing material research for fuel cells, for electrical drives, and for sensor materials. The second large area for quantum algorithms and using quantum computers is machine learning, quantum machine learning. One of the examples is CERN, yeah, with a Large Hadron Collider from high energy physics. And they collect a large volume of sensor data, yeah, in these experiments. And they have applied quantum machine learning to this data and achieved quite, let me say, promising results. And the third area is optimization, like routing optimization, production optimization. And one of our partners who is looking at that is E.ON, in the context of optimization problems related to the energy energy problems. Yeah. Okay, so I mentioned a couple of examples, and all of these companies, enterprises are part of the IBM Quantum Network. And worldwide, we have roughly 250 members in that network. These are enterprises, but also startups, also a couple from Germany who are also here at this event. We have academic partners, and this is the ecosystem, the group in which we want to bring quantum computing forward on that path to quantum advantage. Okay, so now with the charts, we can skip some of them because we already discussed that. Okay, so one of the good news is that quantum computers are real, and since 2016 we have the first real quantum computers on the cloud. In the meantime, we have roughly 25 systems that can be used. and they are used quite extensively. You can see the numbers, a couple of billion quantum circuits are executed every day on these systems. There are several ways to get access to them. There is an open plan, which gives you free of charge access to some of these systems. I will comment on that later. So until very recently, systems with up to 7 qubits could be used for free, and that has changed. I will comment on that later. Then on IBM Public Cloud, you can access systems with up to 127 qubits in a pay-as-you-go mode. So use them and pay per second. There's a premium plan where you can reserve larger chunks of access on these systems. And with the premium plan, people then also become member of the quantum network that I just mentioned. And then there's a, let me say, consulting offering, which includes access to real hardware, education, and identification of industry-relevant use cases, and prototype implementation of such a use case. Okay, so I mentioned at the beginning that our focus is really on useful quantum computing, and practical quantum computing. On the other hand, also, of course, to protect against the risk that quantum computing might bring in the future for security and for encryption. Okay, definition of quantum advantage, we already discussed that. Also the 3 areas mentioned here on the left. And I mentioned also these 250 members in the quantum network. Now we have the roadmap. Probably many of you have seen that before. Actually, it did not change a lot since we announced that roadmap a couple of years ago. What we added is the green check mark every year, saying, okay, also this year, and the most recent update was end of last year, where we said, okay, we also delivered as planned the Osprey systems with more than 400 qubits. And I can confirm this target mark for Condor. So systems with 1100 qubits, we plan to announce that later this year. And there will be an IBM Quantum Summit in early December, so probably that is a good date to watch out for that announcement. On the upper part of that chart, that talks about very important software aspects, and I would like to summarize that as with our midterm vision called frictionless quantum computing. So for application developers from industries, it should be possible, or it will become possible in a couple of years, to use quantum computers just by calling an API without understanding or without the necessity to understand the details of how do quantum algorithms work and how do quantum computers work. Okay, so in the box on the right there, you see mentioned 100,000 qubits. That is not 2026. The column says beyond 2026. And actually we said that we want to develop, together with partners, systems with 100,000 qubits within 10 years. So by 2033. And the Condor systems, they will look different than the systems that we have until now. So the Quantum System 1, that will become a Quantum System 2 with a very different look. Okay, 100,000 I mentioned. Now, if we want to discuss the performance of quantum computers, how can you measure or how can you assess the performance? And I'm a mathematician by training, so I always struggle with this equation here, because it's not a mathematical equation. But I would try to save that in saying that the performance is a function of scale, quality, and speed. And we already discussed scale when we had a look at the roadmap. And for specific industry use cases and specific algorithms, a certain minimum number of qubits is needed to execute the algorithm at all. So scale is important, but also quality. And a couple of years ago, we have introduced a benchmark called quantum volume, that can measure or can describe the quality of systems. So the ability to achieve, although there's error noise in these systems, but still to achieve meaningful results. We will discuss that later because that is a very important aspect. And then the third dimension is the execution speed. And that does not only come from the quadratic, polynomial, or exponential speed up of the algorithm, but also the execution speed of the hardware. Yeah, so like the gate switching times is important, and there are huge differences. So in a bit, we will see in the publication that we did called utility paper. And these calculations ran a couple of hours on our systems. And there are other technologies which are, in that sense, slower, not only by a couple of percent, but in orders of magnitude. Yeah, 1 or 2 orders of magnitude slower, which then means it's not a couple of hours, but days or even weeks. And so the execution speed is very important, and that is where we see a big advantage of superconducting qubits. Okay, so in addition to these 3 dimensions that I mentioned, there are also other aspects like the capabilities and the instructions that you can use. And one example is dynamic circuits. And that means since about 1 year on our systems, you can do a mid-circuit measurement. And depending on the result of that measurement, of some of the qubits, you can change the execution flow. So depending on that, within the coherence time of that circuit execution, you can change the quantum gates that will be executed afterwards. And that has significant advantages in algorithms, so you can reduce the depth of the algorithms, of some of the algorithms. Okay, so now let's get closer to quantum advantage in our discussion. And let me explain this chart. First of all, the axis on the x-axis, that is the complexity of the quantum circuit that you want to execute. So more to the right is better. You want to execute more complex circuits and problems. The y-axis is the cost of the execution or simulation. And so on the y-axis, lower is better. Then let's have a look at the white curve. That is if you use a classical computer to simulate or to run, to execute that quantum circuit. And as we know, with increasing complexity of the circuit, you have an exponential growth. So that is very limited what you can execute or simulate classically. Then let's have a look at the blue curve next. Because a very important concept in quantum computing is called quantum error correction and logical qubits. And that assumes that you can, with some effort, generate like perfect qubits. And of course, you can do many nice things with these perfect qubits, but it is a very significant effort to create these logical and perfect qubits. And the methods, the approaches that are known with quantum error correction, they require a large amount of additional qubits that are used, so many physical qubits that are being used to create a few logical qubits. And as you can see on that illustration, we say that the initial effort for this error correction is very high, and that this is not feasible for the foreseeable future. So for a couple of years out, we think it will not be possible to really practically apply quantum error correction with logical qubits and then run logical gates on top of that. But there is also the green curve, and that discusses quantum error mitigation. And that is a different approach from quantum error correction. It sounds a bit similar, but it is very different. And for quantum error mitigation, you do not need additional qubits, but you need to execute the circuits that you are interested in multiple times and also variations of that circuit. And we will have a closer look at that on the next chart. So with these approaches, as you can see here, we expect that we can get to the lower right on that chart, so right of the white curve. So we will see later that what we said here was today we are here. Actually, we think that we have moved closer to the intersection already, that we are very close to that intersection, not yet on the right-hand side of the white curve. Okay, so how does one of the quantum error mitigation approaches work? So what I will describe is predictive error cancellation, or PEC. And that means that you need to execute additional circuits that are, let me say, similar to the circuit that you are actually interested in. And so what you do is you learn the noise model of this specific circuit on the specific hardware. Yeah? It's not a general noise model. It is really, it depends on the circuit and on the hardware. And you need multiple executions, so a large number of circuit executions. There's also a formula for how many executions are needed. I don't want to discuss that in detail. You can see it's an exponential formula, which has some, let me say, risk. Or on the other hand, the basis of the exponential, the gamma bar, needs to be close to 1. And then this becomes practical. And I will comment later when we think this can be executed for what size of circuits. And we are very close to actually doing that. But let me first speak about an intermediate step that we recently achieved. And that is a publication in the Nature magazine. We call it the utility paper. And that talks not about quantum advantage, but a new term. We call it quantum utility. And so what we did is we looked at a problem from physics, an Ising model that describes the magnetization of a material. And that can be described, or that can be mapped to a quantum circuit with 127 qubits and up to 60 entangling layers. These are really large circuits, if you look at what has been executed before. And that has been compared with classical methods, so classical brute force methods, and also classical approximation methods. And now the statement in that paper is that with a quantum approach, we can go beyond the classical brute force methods, and we are in the same ballpark as the classical approximation methods. So the claim is not that quantum is better already, but in the same league, which is a big step forward. Okay, so if you are interested in more details about that paper, I would like to refer you to a YouTube video that was part of the Qiskit seminar series in, I think, back in July, and that discusses the details of that paper in detail, and also some papers that have been published right afterwards that discuss, let me say, better or improved classical approaches, and how we see that. So in short, we really appreciate these advances that have been made on the classical side, and that is part of the scientific progress. Okay, so now something, a new aspect. Last week, there was another paper published by Boeing and IBM that discusses or that models chemical reactions, in particular corrosion. And there are several blog entries and also a Nature paper. And also in that paper, the researchers say that they are on a similar level as leading classical methods. So that would be another instance of what we call quantum utility. And with that quantum utility, we say that quantum computing is now a reasonable, a feasible tool for scientific research. Not yet for business, but for scientific research, and not only for research that is related to how do I build quantum computers, but really using quantum computers for other kind of research. Okay, so I mentioned that we also want to look a bit into the future, and actually, end of last year, we have announced what we call a 100 times 100 challenge, and that has two parts. So one part is that we say in the next year, in 2024, we will provide a tool stack consisting of hardware and software that will be able to execute so-called 100 times 100 circuits. So circuits with at least 100 qubits and 100 entangling layers, basically error-free, and that within 1 day. So that goes beyond what we have done in the utility paper. The utility paper was 127 qubits, but only 60 entangling layers. And now with that tooling, we want to go up to 100 circuit depths. That is only one part of the challenge. That is kind of what IBM with a few select partners will provide. But the second part of the challenge goes to the whole ecosystem, to the whole quantum computing community. And that is the question, okay, what can I do with this tool stack? So what practically relevant problems can be mapped to a quantum circuit that fits into this 100 times 100 budget. Yeah? And both parts of the challenge are equally challenging, I would say. Yeah? And so the expectation, the hope is that both parts will be kind of solved, yeah, and kind of converge, so that with that we identify practically relevant circuits that can then be executed on these systems. Maybe not next year, so you have to learn how to work with that, but soon after. Yeah? And very important, the basis for this is quantum error mitigation, yeah, and not quantum error correction. Okay, so quantum utility, as I said, that is a new term that we kind of coined, yeah, to describe the state that we are in right now. And we also call the systems, yeah, that are capable of running these circuits in that size, utility scale systems. And that is really where the focus is right now. Yeah, so building, improving, and using these utility scale systems. They are larger than what can be simulated classically. And so this is really, in German I would say, wo die Musik spielt, so where it gets interesting. Okay, and we also announced that we will upgrade our whole fleet of quantum computers that I mentioned at the beginning to 100 and more qubits. So all of the smaller systems will be retired pretty soon. Yeah? And then only systems with 100 and more qubits are available. Yes, so and this chart says they will be available for everyone to use. Now the question is, what does that mean for the open plan, for the access that is free of charge? And yes, both things come together. And since a couple of days, you can access systems with 127 qubits for free, yeah, as part of the open plan. I mean, you can imagine there's a limitation of the amount of usage every month, yeah, but every month you are entitled to use a significant part for free. Yeah. And we think that is really important, yeah, for education and really getting to know systems of that scale and dealing with that error and noise, yeah, and also developing heuristic approaches, yeah, to get meaningful results from these systems. Okay, so and what does that mean for Europe and for Germany? Actually, you probably know that we have one of our real systems is located in Ehningen. And in the first half of next year, we will build a quantum data center. So with multiple systems and all of these systems with 100 or more qubits in Ehningen, yeah, and get that operational. And these systems then can be accessed with that pay-as-you-go model or in that premium access, so buying larger chunks of access to these systems. Okay, so maybe if we have a minute left, yeah, then I have two more charts. So one is information about one of the next quantum events. So there will be a quantum industry exchange in Ehningen on the 26th of October. Yeah, so and you are invited, yeah, to register for that event and to have a look at the agenda. If the QR code does not work, please reach out to me. I can provide you the URL for the registration. And we can have a look at a video with the quantum system 2 that we will announce probably end of this year. Okay, so I hope that was a reasonable overview of the status of quantum computing and how we see the path into the future. Okay, so if we have time for a question, then happy to answer one or two questions.
Yes, over there. Oh, that's going to be a complicated one. At the very end.
Hi, Jan. Thank you for the speech. You mentioned the quantum computer in Ehningen. So what is planned with the system? I think it's 3 years old now. So what are the plans for IBM and for Baden-Württemberg with this more or less old system now?
Yes. So what I can say is that in Ehningen we will have multiple systems with more than 100 qubits, yeah, and access with that. So access through IBM you can get with that pay-as-you-go model or with premium access. And we will have partners who also have access to that system and can kind of resell that access. Yeah. So I mean, currently, you know, the system that is currently in Eningen can be accessed through Fraunhofer only. Yeah. And I think we can assume that that will continue, that access path. And you probably you also have heard about our partnership with T-Systems. And T-Systems also will provide access to real IBM quantum computers, probably including these ones that will come to Eningen.
Thank you.
Thank you for the talk. So yeah, qubit count, of course, is a very important number, but could you maybe also comment on how the error rates of the CNOT gates are developing?
Yes. Yes, so very important aspect. Yeah, the quality is really key, and we are very transparent with that. So on one of our website, quantum-computing.ibm.com, you can see all of the quantum computers with the daily calibration data. Yeah, so for each single qubit, you can see the coherence times, error rates, everything. Yeah, and that is updated daily at least. Yeah, so there you can see the concrete numbers. And I can comment on the high level.
Sind denn alle da jetzt?
So always when we announce a new larger system, then in that step the focus is on scale. Yeah, so on the number of qubits. And then typically after that there are multiple releases of that chip. Yeah, so we have seen that with the Eagle systems, with the 127 qubits, there are multiple releases, and with the releases, then the focus is really on quality and on execution speed. Yeah. So definitely, I mean, also you have seen that with the Condor system, with the Osprey system, with the 400 qubits, that the first release is like a step back in quality, but that will be improved in the next releases. Yeah.
Like in which kind of scale? I mean, I've been checking these numbers for, I don't know, like maybe 2 years, but I felt like they are somehow a bit stuck, like at 1%. So I don't know, like, is there any development or?
Yes. Yes, so there's a focus on improving that. For example, coherence times. Yeah, you have coherence times of in the ballpark like 200, 300 microseconds. And we already have test systems with more than 1 millisecond coherence times. Yeah, and that will be rolled out and integrated into the production systems as well. Yeah, and similar is true for the error rates. Yeah, single qubit, so measurement errors, multi-qubit gates, and so on. Yeah, but I cannot comment on concrete numbers for that.
All right, thank you.
Und Frau Aswald?
So I don't know if you are allowed to comment on that, but the technology this is based on will stay on the Transmon qubit, and also is planned for the qubit for the future to stay on the Transmon platform.
Yes. So we are closely monitoring and looking at and doing research also for other qubit technologies. Yeah, especially the team in Zurich is working on that. They are also doing publications on that. But looking at these 3 dimensions, scale, quality, and speed, we think that in this combination, superconducting with transmons is the best way into the future.
And also a question regarding the timeline, where you mentioned the scaling over the next years. So what would be the timeline to really achieve then the final quantum advantage at the end?
Yes. So, I mean,
dangerous question to answer.
Yeah, yeah. So, I mean, that is not a question of development. Yeah. So, this many lines of code, that many person days are needed to achieve that. It's really research questions, and we even do not know all of the questions. Yeah, and even not the answers. So, there's a high uncertainty with that. But so the hope is really that with the 100 times 100 challenge, yeah, that both parts will come together. Yeah, and so we want to provide the tooling next year, 2024. And then, soon thereafter, yeah, hopefully to achieve quantum advantage for the first practically relevant use cases. Yeah, that does not mean for all of the 3 areas. Yeah, it will be a first instance, right? But that is the idea in a few years. Yeah.
I hope there are no more questions, Jan, because
That's good.
we're running out of time. No, thank you so much. And honestly, he did an amazing job talking about his presentation without having the presentation. So come on, give him a last applause.
Thanks a lot.